Greetings everybody, we are back here once again, more complex analysis. It is not stopping this holidays, isn't it? I have too much time on my hands, so plenty of time to make these little complex analysis videos for you guys. So what are we doing today? We're taking a look at the integral from 0 to infinity of cosine of ax minus cosine of bx over x squared. So it's actually not a particularly challenging integral, I would say. We've done much more difficult integrals on this channel. So this is a rather simple one that most people who do complex analysis should be able to evaluate. It's pretty similar in style to the integral of sine x over x, and I think one of the other ones I've done on this channel. So let's just jump straight into it. By the way, A and B are positive. We might use that later. So how can we get started here? Let's first of all define for ourselves a new complex function f of z. So I'm going to let over here a new function f of z be equal to. Now, what should we choose our function to be in this case? Well, we have two cosine functions. Usually we don't like to work with cosines or sines in the complex plane. We like to work with complex exponential functions. So I'm going to replace cosine of a times x with e to the I times a times x, not x, actually z. And then we're going to have a minus e to the I times b times z, all divided by z squared. This is going to be the complex function we integrate, and this will reproduce our integral that I'll call I at the very end. Now the next thing we'll notice is that we have a pole over here at exactly z equals 0. So I guess it is in indeterminate form right now. If you take the limit as z approaches 0, you can't really get anywhere. But if you do one round of L'Hopital's rule and then you try to approach 0 again, then this thing will, have a singularity at 0. So there's going to be a pole here. So let's see what our contour should look like. So we're going to draw up the complex plane here. As you can see, I already tried doing it and it turns out horribly, so I'm doing it again. So here's our complex plane. We have a pole at 0. So I'm going to use some red chalk over here, mark with the nice x here. So here's our pole at 0. And what do we want to do? We want to integrate from 0 to infinity. Okay, so we'll start, well, we can't really start at 0. We'll start at some distance epsilon away, and then we'll integrate up to some bigger radius. Let's call it r here. Okay, so this is the real axis. And well, we want to do some contour integration, and it turns out if you take the same interval and you reflect it onto the negative real axis, then you're going to get something nice to integrate, which we'll see later on. So we have these two parts, and then what we'll do is we'll just enclose this, not really enclose, but go around the singularity with a little semicircle, and then we can complete the contour just by doing a big semicircle that goes all the way around to a semicircle of radius r. So this is the contour integral that we usually use for integrals going from 0 to infinity or minus infinity to infinity. So this contour, we'll call this a c. We'll call the part of gamma in here little gamma. We'll call the big semicircle, we'll call that big gamma. And then, we have the intervals down over here. So this is our setup. So we can also write down a few integrals to get us started. First of all, if you take a look at the contour integral over c, well, notice our function is going to be analytic everywhere inside of this contour. Exponentials are fine as they are. This z squared only produces a problem at 0, which we don't include. So everywhere inside of c is 0. So by Cauchy's theorem, we have that the contour integral, that's going to be equal to 0. So contour integral of f of z. So we can decompose this guy into each of these separate parts here. Let's say the integral from minus r to minus epsilon, and then plus the integral from epsilon to r. I don't bother writing the f of z's over here because it's implied. And then we also have the plus the integral over little gamma, and then plus the integral over big gamma to finish off. So these are all the integrals we're going to evaluate here. So now all we have to do is just, evaluate them one by one and see if we can reproduce our integral I here somewhere. Okay, so let's first of all start off with the integral from epsilon to r and minus r to minus epsilon. We'll kind of do these two together because they'll produce something quite nice, and you'll see it in just a second. So first of all, let's take a look at the integral from epsilon to r, and then plus the integral from, minus r to minus epsilon. Let's see what this gives us over here. Now the integral from epsilon to r, I'm going to leave this guy untouched, so it's just going to integrate the function f of z. So epsilon to r of f of z, and then we have a dz. But what we're going to change is this integral from minus r to minus epsilon. So on this integral over here, what we're going to do is we're going to introduce a little change of variables because there's negatives everywhere. That's not too nice. So basically just going to perform a reflection back to the positive real axis. And we can do that using some substitution. Let's say let t be equal to minus z, that's going to reflect everything. So dt, that's going to be equal to minus, and then we have a dz. So we'll do the substitution on this integral over here. So what will that give us? That's going to give us plus the integral. Now minus r, that's going to become positive r. Minus epsilon, that's going to become epsilon. And then we're going to have f of minus t over here. So originally it was f of z, it's going to become f of minus t. So what is f of minus t? It's going to be precisely e to the minus I times a times t, and then we have minus e to the minus I times b times t. Okay, so we put negatives everywhere, and if you substitute z equals minus t down there in the denominator, that's just going to be t squared because negative squared is positive. Now our dz over here, that's going to become a negative dt, so we put this guy at the very end over here. So this is what we have so far. What we can do is we can take this negative, and we can put it into this integral to change the bounds. And this is really quite nice because the bounds are going to match up with this integral over here. And since the bounds match up, we can just add the integrands together. So let's see what this gives us over here. We have the integral from epsilon to r. What is f of z? Well, I'm going to replace z with, let's just do t here, just so the variables match up. So f and t dt. That's going to be e to the I times a times t minus e to the I times b times t over t squared. Okay, so that's the f of t there. And because we use this negative to switch the bounds, we can just add this integrand in as well. So we have plus e to the minus I a t, and then minus e to the minus I b t, all divided by t squared, and then we have a dt. No negative here because we distributed it in. All right, so from here, what can we do? We can combine the fractions together, but I'm going to kind of reshuffle the terms a little bit. Notice that we can write it as follows. We have the integral from epsilon to r. Now, what can we do? We have e to the iat, and I also want to pair it up with this e to the minus at. So I'm going to write that first. We have e to the I times a times t, and then plus e to the minus I times a times t, and all this is still divided by t squared. Okay, and then we have the I times b times t and so on. Now, there is a negative here and also a negative over here. So I'm going to factor out that negative. So we have negative e to the I times b times t, which was this guy. And then because we factored out the negative, that's going to become positive. And then we have e to the minus I bt. And all this is divided through by t squared. All right, and then we'll finish it off with the dt. Okay, so why did I do that? It's because if you take a look at these pairs of exponential terms here, we have e to the I times something, and then e to the minus I times the exact same something. And same goes over here. And that's perfect because that looks like almost a cosine function. All we're missing is just a 2 in the denominator. So let's say we want a 2 down here. We can't just write 2. We also have to multiply the numerator by 2, so everything stays the same. So let's just put the 2 right out the front here. And basically, now we have cosines everywhere. So we can rewrite this a little bit. This is going to be equal to 2 integral from epsilon to r, okay? And then we're going to have the cosine of what? It's at, because it's the thing without the I, pretty much. So that's at divided by, well, t squared at the bottom here. But we also have this negative cosine, so we might as well write that in. So minus cosine of b times t, and this guy is divided by t squared dt. Okay, and this is starting to look a little familiar because we have integral cos at minus cos bt. Well, that's basically this integral, but we just replaced the variables. And now notice we're going to take epsilon and r to infinity in the end anyways. So taking the limits over here as epsilon goes to 0 and r approaches infinity, that's going to recover to integral from 0 to infinity, but that's as going to reproduce our I. So that's really quite nice over there. If you integrate along the real line over here, well, excluding the singularity there, you're going to reproduce 2I. So that's quite nice. So let's take a look at some of the other integrals now. So we've gotten these two guys sorted here. Let's take a look at the integral over, say, little gamma here. And this one's going to be pretty fun, in my opinion. Now, sometimes when you do these gamma integrals, they tend to vanish, but that's only when you integrate around branch points and you take the limits as that little circle gets smaller and smaller. But we're enclosing, or we're going around a pole over here, so it's not going to produce at 0 at all. It's going to give us some nice number, probably. So let's take a look at the integral over gamma of our function f of z dz. So first of all, we do need to parameterize this guy. The parameterization is rather quite simple. It's just going to be, well, this is a semicircle centered at 0, radius of epsilon, so we can parameterize this guy by epsilon e to the I theta. And I guess we'll write the parameterization. Let's just put in this little space up over here. So make a little space for our parameterization. So on gamma, our z's can be written as epsilon e to the I theta. And if you differentiate both sides, that's I epsilon e to the I theta, and we have a d theta. And where is theta going between? Well, it's going to go from, well, I forgot to tell you which way we're going. We're going anti-clockwise, so positive direction. So this gamma is going to start at pi and end back at 0. So we're going to go from pi back to 0. So let's see what this gives us over here. So plugging in the parameterization, we have the integral from pi back to 0, and then now f of z. Instead of z, we're just going to plug in epsilon e to the I theta. So let's see what that gives us over there. We're going to have, first of all, e to the I times a. Now, originally z went there, but now we're going to have epsilon e to the I theta, and then we have negative e to the I times b, epsilon e to the I theta, and all of this is divided through, well, there was a z squared down here before, but now it turns into epsilon e to the I theta, this whole thing squared, and then our dz, that turns into I times epsilon e to the I theta, and then we have a d theta to finish off. Okay, now something nice happens here. In particular, we have 2 copies of epsilon e to the I theta, 1 copy up over here, so we have this square will cancel with this term over here. And what does that leave us with? Well, we can factor out that I over there, and we're going to have I integral from pi back to 0, and we can put a negative here as well because I want to change the bounds as 0 to pi. And we're just going to have e to the a, ia epsilon e to the I theta, and then the same with the other one as well. And this whole thing, that's also still divided by epsilon e to the I theta, and then we finish off with a d theta, like so. Okay, and here's where we have to do some complicated things here, because we have an epsilon in the denominator here. That's not really that great, because as epsilon approaches 0, this might blow up potentially. Well, it's probably not because we have some things going on in the numerator there, but what you could do if you're doing this very unrigorously, like I do sometimes, you could take the limits as epsilon approaches 0 into the integral, and then you could use some L'Hopital, I guess, in there, and you'll get some answer. But if you want to do this properly, this is a good opportunity to do that. What you can do is, well, we really want to cancel this epsilon e to the I theta in the denominator there. You'll notice we have epsilon e to the I theta in these exponents. So it turns out if you Taylor expands these exponential terms here, then you're going to be getting, well, polynomials in epsilon e to the I theta, and those will cancel epsilon e to the I theta down over here, which is exactly what we want to do. So Taylor expanding those exponentials is a good way to go here. So we have, what do we have? Negative I integral from 0 to pi. Now, I'm going to write 1 over epsilon e to the I theta, and then we're going to start Taylor expanding both of those exponentials. So we have our first exponential guy over here. How can we Taylor expand that? Well, that's going to be the sum running from, let's choose an index, let's say n, goes from 0 up to infinity. And what do we have? We have the exponent of that, so that's I a epsilon e to the I theta. This guy is raised to the n. This is divided by n factorial, and that completes our first sum. And then our second sum, well, that's negative, we have the sum running from m equals 0 to infinity. And then we're going to have I times b this time, epsilon e to the I theta. This is raised to the mth power, and all this is divided by m factorial, and then we can close off square brackets, and we have a d theta. So this is what we get if we Taylor expand everything. So it looks rather quite complicated, but here's where things start to get slightly simpler. First of all, notice one nice thing. What happens when n is equal to 0 and m is equal to 0? Well, if you plug n equals 0 into here, well, something to the 0 is 1 over 0 factorial is 1. Same thing over here, you're going to get a 1 here. So in fact, when n and m are equal to 0, that's completely redundant because the summands will basically cancel each other out. So there's no need to include m equals 0 and n equals 0. So we can start our index at 1 here. Now, what else happens? Notice we have polynomials in epsilon e to the I theta now. That's going to cancel with this guy at the front over here, which we wanted to get rid of. So what we can do is we can rewrite this a little bit, and we can rewrite this as negative I. We have the integral from 0 to pi. We get rid of this guy because we're going to cancel with some of those epsilon e to the I thetas now. So first of all, we're going to have the sum running from n equals 1 up to infinity. We're going to have I times a raised to the n, so that's untouched. But now this guy, that's going to reduce by a power of 1. So this is epsilon e to the I theta raised to the n minus 1, and this is still divided by n factorial. And for the second sum, we have the sum running from m equals 1 to infinity. We have I times b raised to the m, that's untouched, but now because we cancel this guy, that's going to become epsilon e to the I theta raised to the m of minus 1 now, and this is divided through by m factorial, and we can wrap up the brackets here, and then we have a d theta. So that's really quite nice there. We've gotten rid of that troublesome epsilon on the denominator. So the next thing we can do, since these are just, well, sums now, they're just polynomials, and we just have a definite integral out the front, we can bring that definite integral into each of these sums. And what should we get? Well, we're going to get the negative I out here. We have big brackets, and first of all, what happens on this sum? We have the sum running from n equals 1 to infinity, I times a to the n, over n factorial, and let's see, we have epsilon to the n minus 1, and then integral from 0 to pi. We're going to integrate that exponential, so e to the I theta, and I guess we have to have n minus 1 here as well, d theta, and we can bring the integral into the second sum as well, so minus the sum running from m equals 1 to infinity, I times b to the m, we have epsilon to the m minus 1, and then this is divided by m factorial. Then we can have the integral from 0 to pi of just this exponential guy here, and then we have m minus 1 d theta, and that's it for that sum, and then we close off that brackets as well. So quite a mess going on right now, but let's remain hopeful that something nice comes out of this, because notice our epsilons are outside of our integrals now, which means that we can just apply the limit directly to these epsilons, which is quite nice. So what on earth happens as epsilon approaches 0? So we put that on the final line, limit as epsilon approaches 0. What's going to happen here? You may say, well, everything's just going to 0 because we have these factors of epsilon everywhere, and yeah, we're just going to get 0. But if you take a look carefully, this is an m minus 1, and this is an n minus 1, and we're starting our indices at 1. So what happens when m and n are equal to 1? Well, let's take a look at m first. When m is equal to 1, this is epsilon to the 1 minus 1, which is, wait a minute, that's 0. So in fact, there's no epsilon when m and n are equal to 0. So for all the other terms, m equals 2, m equals 3, n equals 2, n equals 3, and so on, we're going to have these epsilon factors. So as epsilon approaches 0, all those terms are going to vanish. However, when m and n are equal to 0, we're not going to have epsilon, so there's something that survives there. So in particular, as epsilon approaches 0, we're only going to keep these terms when m and n are equal to 0. So what happens when n is equal to 0 here? Well, this is something to the 0, which is 1, and then 0 factorial, that's also 1. So nothing really happens there.
One eternity later.
Well, first of all, this is I times a to the 1, so we're going to have, just I times a over 1 factorial, so I guess that's just I times a. I also forgot this negative I out the front here. So first of all, we have I times a. Epsilon, that doesn't exist. It's just going to become 1 because n is 0. What happens to this integral over here? Well, as you can see, we have n, but n starts at 1, so this is e to the 0, which is 1. So that's just going to become integral from 0 to pi of d theta, which is, well, that's pi. And then on this guy, we have negative I times b to the 1. That's going to be I times b. And then epsilon, that disappears when m is equal to 1. And again, this integral m minus 1 is 0. So we have e to the 0 is 1. Integral from 0 to pi, well, that's just going to be exactly pi. And that's basically it over there. We can factor out I times pi, and if you multiply by this negative I out the front, that's just going to be 1 times pi. So we have pi overall, and then a minus b. And that's basically it over there. So pi times a minus b, that is the integral over gamma as our epsilon approaches 0, which is really quite nice. So final integral over big gamma, and this one's just going to go to 0. I might as well do it here for you guys just to make this video complete. And I've done this a few times on the channel already with the exponential functions and so on. We might as well do it here while we have the time. So finally, this is the blackboard where I have to kind of hold it down all the time because it doesn't like to stay still. I think the engineers didn't quite build this blackboard right, or something's wrong, I don't know. So let's take a look at the integral over gamma. So this one we want to estimate, so let's put absolute values around it. So what exactly is this going to be? This is the absolute value of the integral. So we need a parameterization for this. So how do we do that? Well, on big gamma over here, z is equal to r e to the I theta, where r is our big radius. And what is dz? dz is just going to be I times r e to the I theta d theta, and theta, that's going to go, well, we're starting here, so that's an angle of 0. We're going all the way to pi, so theta is going to go from 0 to pi over here. So let's plug that parameterization into our integral. So we have integral from 0 to pi of our function f of z, which is going to be e to the I times a times z, but that's r e to the I theta, minus e to the I b this time, r e to the I theta, and all of this is divided by, well, we have r e to the I theta squared, so that's z squared, and then our dz, that becomes I times r e to the I theta, d theta. So very similar to before, there's a factor here which cancels with the squared here, and this is in absolute values. We can factor out this I, but because of the absolute value, that just pretty much vanishes. So what are we left with over here? We're left with, well, this is equal to. Actually, I wanted less than or equal to inequality because we're going to bring these absolute values into the integral using that integral inequality there. So this is less than or equal to integral from 0 to pi. What are we going to have on the inside? Well, absolute value of e to the I a r e to the I theta, and then we have a minus e to the I b r e to the I theta, absolute value divided by what goes on down here. Well, absolute value of r is r, absolute value of e to the I theta is, well, that's just 1 because we're on the unit circle. So this is r here. Don't need absolute values because r is positive. And we have a d theta to finish off. So as you can see, we have absolute values of something and another something. So let's just use the triangle inequality here to split things off a little bit more. So we have less than or equal to, we bring the 1 over r out, and then let's see, we have the integral from 0 to pi, absolute value of e to the I times a times r, e to the I theta, in one absolute value, and then triangle inequality, we have the absolute value of the other guy, which is e to the I times b, and then r e to the I theta, and inside absolute values d theta. Now these guys over here in absolute values, we can bound them a bit further, and I'll show you guys how here. First of all, we do need to make one little manipulation, so I'll put it over here. So let's take a look at e to the IA or e to the I theta. How can we rewrite this a little bit? So e to the IA or e to the I theta. Well, notice e to the I theta, what happens if you use Euler's formula on that one? So that's going to be e to the I times a. We have the r, then first part of Euler's formula is cosine of theta. So let's put that guy there. Okay, but then we also have, well, the I times the sine of theta part. So notice there's going to be two i's, which will produce a negative. So we're going to have e to the minus only a over here, then r sine of theta. So hopefully you guys agree with that step over there. So there's two exponentials, we can split it up in their own little absolute values. Now, notice this guy over here, we have e to the I times a, r cosine of theta. Now a, r cosine of theta, this is a real number. So if you have e to the I, a real number, inside of absolute values, then the whole entire thing here is just going to be equal to 1, because you're on the unit circle, which leaves you with e to the negative a r sine theta. But this guy, since this is an exponential, this is greater than 0. You have real numbers over here, so e to a real number is a real number greater than 0. So in fact, you can remove the absolute values there and you ignore this guy over here because it's 1, leaving you with e to the minus a r sine of theta. And you can do the same thing with this b over here. You just replace a with b's and so on. But now I want to start estimating this guy. In particular, if we plug this guy back into this integral, let's actually do that and see what we get. So this is equal to 1 over r integral from 0 to pi of e to the minus a r times sine of theta, and then you also have plus e to the minus b r sine of theta d theta. I just want to take a look at one thing. It has to do with the symmetry of the sine function. Let's draw it over here. So what does the sine function look like? So let's draw the x and y axes over here, so not the complex plane for once. The sine function, well, it looks something like this on the interval 0 to pi, and has the height of 1 over there, and there's this nice line of symmetry at precisely pi on 2. All right, so this point up over here, this is pi on 2, and then comma 1, and then we're symmetric. Now, because the sine function is symmetric and we're integrating our theta from 0 to pi, well, that's really the same thing as going from 0 to 2 pi, but then you just double the whole entire integral, because the integral from 0 to 2 pi is the same as the integral from pi on 2 to pi, because of that symmetry. So in fact, I can replace this pi with just pi on 2, but then I have to multiply the whole entire thing at the front by 2 to compensate for that. That's a nice thing we can do. Now, why do we want to change the bounds there? It's because we want to estimate these exponential terms a little bit more. It's a little bit funny. You could argue that, well, this integral here is finite, and then you have 1 over r there. But sometimes you might not have this r here, so I might as well show you guys what happens if you don't have the r and you want to estimate things slightly further. What you could do is you can say, well, sine of theta. Notice if we construct a line from the origin to that turning point there, then sine of theta is always greater than that line. So what exactly is this line? Well, the height is 1, so the rise is 1, the run is pi on 2. So in particular, this line over here, this is y equals 2 over pi times x. So we make an extra observation down over here. So the observation is that the sine of theta is greater than that function I just showed you, which is 2 over pi times theta, when theta is on the interval 0 to pi on 2. But that also tells you that a times r times the sine of theta is greater than 2 over pi times a times r times theta. And then this tells you that minus ar, sine of theta. Now, a times r, that's positive because a is positive, r is also positive. This tells you that minus a times r, this is actually less than or equal to negative 2 over pi, a times r times theta. And finally, you can put all this inside of an exponential. So if you exponentiate both sides, the exponential function is increasing, so it preserves this direction of the inequality. We have minus ar sine of theta being less than or equal to e to the minus 2 over pi times a times r times theta, like so. So what you could do is from this line over here, you could estimate the integral even further. You can say this is less than or equal to 2 over pi integral from 0 to pi over 2. And then instead of these exponential terms over here, you just write this guy, which is the e to the minus 2 over pi. We have a r and then theta, like so. And then you also have, plus e to the minus 2 over pi, and then b r theta, t theta. And what you get exponential functions. These guys are bounded on the interval 0 to pi on 2. So it's integrable, or Riemann integrable, so it's going to produce some finite number. So this thing is less than infinity. So in the limit as r approaches infinity, because of this r in the denominator here, this is just going to approach 0. And if you are concerned about these r's up over here in the exponential function, you'll also notice that as r approaches infinity here, these exponentials are going to keep decaying, and you can even integrate this. This is something you can integrate using real methods, and you can get some complete results, and you can take the limit as r approaches infinity there if you wish, but I think that should suffice for now. Okay, so what did we just find? So let's rewrite this equation, so let's put it over here. So what does this tell us? We have a 0 is equal to integral from minus r to epsilon. Well, these first two integrals over here, we showed on the first blackboard, this reproduced exactly 2i. So this is 2i here. What did the integral over gamma give us? It gave us something like, now I forgot what it gave us. It was pi and then something. We have pi, I don't know if you guys can see that there. It gave us pi times a minus b. So let's write that in. We have a pi a minus b. And then the integral over big gamma, we just showed that it's equal to 0. So it contributes nothing to our integral. So in the end, how do we solve for I? Well, we can just bring this pi a minus b onto the other side. And because it's going to pick up a negative there, we can switch the order of a and b around and then finally divide by 2. So in the end, what does this tell us? It tells us that I is equal to, well, that's going to be pi over 2. And then we have b minus a. And that does it for this video. That's the final result. So nice and simple result. As you can see, if a and b are equal to each other, you're going to get 0 there, which is what you're expecting. If a and b are equal to 0, you get cosine minus cosine, which is 0. So that's the final result for today's integral. Pretty nice integral, nothing too tricky, I think. But hopefully you guys enjoyed this one. If you do have any integral suggestions, feel free to let me know in the comments below, or you can email me whatsoever. And hope you guys enjoyed the video. Until the next one, have yourselves a wonderful day, and I'll see everyone later. Bye bye.